Welcome to Chapter 4, where we will be discussing the postulates of quantum mechanics. These are the fundamental ideas that underlie quantum mechanics. We've seen a lot of these ideas already in Chapter 3 when talking about the particle in a box and the things that we can learn from it. But here we're going to formalize this and talk about sort of what are the fundamental postulates that underlie all of quantum mechanics. And so a lot of these are ideas that can't necessarily be proven, but are taken as sort of the facts that we start from and build up the rest of quantum mechanics from. So we'll go through these in order. This is a numbered list, and we'll start with postulate number 1. So postulate number 1 is that the state of a system is specified by the wave function. All right, so we have this wave function. Now, it doesn't tell us a lot about the wave function, just that there is such a thing as a wave function. And the other postulate is that psi star psi is equal to the probability distribution. Okay, and so this postulate states that all the possible information we can get about the system comes from this wave function. And we don't know a lot about what this wave function represents, except for that the square of the wave function with the complex conjugate in there is the probability distribution. Now there's some properties about the wave function that are part of this postulate. Number 1 is that psi must be normalized. Right, meaning that we've seen this idea already, but the integral of psi star psi, and down here for the limits on this integral, just put all space. What this means for different systems is going to be slightly different depending on what coordinate systems we're using, so I'm just going to keep it very generic here. And in terms of the variables over here, we'll use the symbol d tau to represent all the variables, whatever they may be. So this could be x, y, and z. It could be just x if we're dealing with a one-dimensional system. We'll see r, theta, and phi show up, and this integral has to be equal to 1. So that's the one of the properties of the wave function that needs to be satisfied for it to be a proper wave function according to this postulate. The second part of this is that the wave function must be well behaved. I'll put that in quotes. Right, we can't have any naughty wave functions, only well-behaved ones. Those are on Santa's nice list. What this means specifically is that psi and the derivative of psi, with respect to all the coordinates, I'm just going to put x here, but this would be all the coordinates, right, x, y, and z, or r, theta, and phi. These, both the wave function itself and the derivative of the wave function, have to be single valued, continuous, meaning that you can take a derivative at all points along the wave function. There's no sudden jumps in the wave function, and finite. Right? It has to be bounded. It can't just increase forever to infinity. And this finite part of it goes with psi being able to be normalized, right? If the wave function is not finite, if it blows up and it's infinite, it's impossible to normalize the wave function. All right, so must be, we'll say, normalizable. It's quite a fun word to say. Okay, and let's just go over single valued is the only one I haven't talked about. If we plot the wave function or its derivative, a single valued wave function is something that only has one value of y for every value of x. Right, so an example of a non-single value wave function would be if I erase this and we had a function that kind of doubled back on itself and went like this. So most of the functions that you're familiar with don't do this. So it's a pretty strange function that is not single valued. Right, so this is not allowed. That would be a naughty function that can't be a wave function. Okay, and so just as a quick check, I have a poll that I usually ask in class. Let's consider this function e to the minus x. And whether a wave function is well behaved or not can depend on what range we're considering. So let's look at this function e to the minus x. If we take e to the minus x from 0, so from x equals 0 to positive infinity, is this well behaved? So I want you to go ahead and pause the video and take a chance to think about this. Maybe go ahead and plot this. If you don't have a graphing calculator, you can pull this up in Google. You can actually plot functions in Google, say plot e to the minus x from 0 to infinity. Another useful resource is wolframalpha.com. You can also do plots there. So, is this a well-behaved wave function? Go ahead and pause your video. So hopefully you've paused, thought about this, come back. This is a well-behaved wave function because if we go ahead and plot this, e to the 0 is 1, and anything larger than x equals 0 will give something even smaller than 1, and it'll decrease exponentially. I mean, by definition, exponential. So this one is a well-behaved wave function. It's finite, single-valued, and it is continuous. There's no point where we can't take a derivative along here. But if we change this to be from negative infinity to positive infinity, right? So if we take all the possible range of x, is this still well behaved? So go ahead and pause your video and think about this one. All right, hopefully you took a chance to think about that. Once we increase the range to include negative x values, if you plot this, what you'll see is that this is not finite when you go to the negative side. And so because this is not finite, if we take this whole range, this is not well behaved. All right, so that's postulate 1. So in the next video, we'll look at postulate 2.